Hi, everyone. In this lecture, we're going to be talking about Charles' law, which is the relationship between temperature and volume of a gas. So, in a nutshell, if you increase the temperature of a gas, you also increase its volume. A common example of this is hot air balloons. So, a hot air balloon heats up the air, and the air takes up a larger volume, it expands, becomes less dense, and the balloon rises. This is named after a famous scientist, Charles, who discovered this relationship. And so the temperature of a gas is directly related to its volume. Now, when you're doing this comparison, the pressure can't change and the number of moles of the gas can't change. So pressure and moles are constant. We're only changing temperature and volume. And so as you heat up a gas, its volume also increases. Or if you cool it down, the volume decreases. Now, I gave you this combined gas law in the previous video. And so we'll use this and we'll simplify it to derive Charles' law. So if we're assuming that pressure and the moles of the gas don't change, then we can eliminate pressure and we can eliminate moles because they're not changing, they're constant. And so we simplify the expression as V1 over T1 equals V2 over T2. And this is Charles' law. So it's only comparing volume and temperature, and we're ignoring pressure and moles. Let's do a practice problem. So a balloon has a volume of 785 milliliters at 21 Celsius. If the temperature drops to 0 Celsius, what is the new volume of the balloon at constant pressure and moles? So we're going to use Charles' law. V1 over T1 equals V2 over T2. Now, they give us some values here, right? They give us an initial volume of 785 milliliters. They give us initial temperature of 21 degrees Celsius. They give us a new temperature of 0 degrees Celsius, and the new volume is what we are looking for. Now, whenever we're doing these, we have to be in Kelvin. So don't forget to convert to Kelvin. So to convert to Kelvin from Celsius, you always add 273. 21 plus 273 is going to be 294. And 0 plus 273 is just 273 Kelvin. And so we'll be using those values for our equation. So let's plug our numbers in here. So volume 1 is 785 milliliters. Temperature 1 is 294 Kelvin. New volume is what we're looking for, and the new temperature is 273 Kelvin. To get volume 2 by itself, we have to get rid of this 273 on the bottom. So if we multiply both sides of the equation by 273, it'll cancel on this side. And so volume 2 is going to be equal to 273 times 785 divided by 294. If we're paying attention to units, Kelvin will cancel Kelvin. And the only unit we'll be left with is milliliters, which makes sense because we're solving volume. Let me punch this into a calculator. 273 times 785 divided by 294. And I get about 729 milliliters. Which makes sense because we're going from 21 Celsius to 0, so we're cooling it down. And so as temperature decreases, volume should also decrease, which makes sense. So our volume is smaller than the original. These next couple slides are just the solution. So 729 looks like we did it right. Let's do one more. Sample of oxygen gas has a volume of 420 milliliters at a temperature of 18 Celsius. At what temperature will the volume of the oxygen be 640? Pressure in moles are constant. Well, once again, V1 over T1 equals V2 over T2. Now, they're asking us at what temperature will the volume of the oxygen be 640? So what's given? We're given an initial volume of 420 milliliters, an initial temperature of 18 degrees Celsius. Let's convert that to Kelvin. So plus 273 is going to be 291. The final volume is 640 milliliters, and the final temperature is what we are looking for. Now, before I plug these values in, let's just do the algebra first in variable form and then plug the numbers in last. So we're trying to get T2 by itself. It's currently on the bottom of a fraction, so we need to get it into the top of the fraction. I'm going to multiply both sides of the equation by T2, and it's going to cancel over here. So we're going to have T2 times V1 over T1 equals V2. So now we've got T2 to the top of the fraction, but we still need to get it by itself. So I'm going to multiply both sides by the reciprocal here. So times T1 over V1 to both sides. And the T1 and the V1 will cancel. And so we're left with T2 is equal to V2 T1 over V1. And now that we have T2 by itself, we can just plug our numbers in as they are. So volume 2 is 640 milliliters. Initial temperature is 291 Kelvin. And the initial volume was 420 milliliters. Milliliters will cancel. We'll be left with Kelvin, which makes sense because we're solving for temperature. So plug that into a calculator, 640 times 291 divided by 420. I get 443 Kelvin. But they wanted this in degrees Celsius. So to convert that back to Celsius, we subtract 273. And I get 170 degrees Celsius. And it looks like we did it right. So once again, Charles' law is comparing temperature and volume. And from the combined gas law, if pressure and moles don't change, you can simplify the expression, and this is known as Charles' law. Thanks for watching. I'll see you in the next video.